Preparing for a battery engineer interview questions and answers interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How does a lithium-ion battery store and release energy? A lithium-ion battery stores energy by moving lithium ions from the cathode into the anode during charging. During discharge, ions travel back through the electrolyte while electrons flow through the external circuit, powering the load. The anode, cathode, separator, and electrolyte each have distinct safety and performance roles. Cell voltage depends on electrode potential differences, while capacity depends on active material quantity. I would also mention that irreversible side reactions reduce usable life. While answering, explain lithium-ion movement, electron flow through the external circuit, anode and cathode roles, electrolyte function, charging versus discharging, and how cell voltage relates to electrode chemistry. Question 2. What factors determine a battery cell's energy density and power density? Energy density measures stored energy per unit mass or volume, while power density measures how quickly that energy can be delivered. Energy density improves through higher voltage chemistry, greater active material loading, and lighter packaging. Power density depends heavily on low internal resistance, conductive pathways, electrode thickness, and thermal management. Thick electrodes may increase energy but slow ion transport. Therefore, I select the design according to the application, because an electric vehicle and a power tool need different balances. Make sure to cover gravimetric and volumetric definitions, electrode loading, cell voltage, internal resistance, active materials, thermal constraints, packaging, C-rate capability, and the trade-off between energy and power performance. Question 3. How would you select a battery chemistry for an electric vehicle application? I would begin with vehicle requirements: range, acceleration, fast charging, usable life, climate, packaging, and cost target. NMC can offer strong energy density, while LFP generally provides excellent safety, cycle life, and cost advantages. I would compare full cell performance, not just chemistry data, including thermal behavior and aging under the actual drive cycle. Then I would validate the choice through abuse testing, module integration, and total pack economics rather than selecting chemistry from energy density alone. In your answer, discuss energy density, power capability, cycle life, calendar life, safety, cost, temperature behavior, raw material availability, charging requirements, and application-specific duty cycles. Question 4. What is the purpose of a battery management system? A battery management system keeps the pack within safe operating limits while maximizing usable performance. It measures cell voltages, pack current, and temperatures, then estimates state of charge, state of health, and available power. The BMS controls contactors, limits charging or discharging, balances cells, records faults, and communicates with the vehicle controller. I would design independent protections where appropriate, because software estimation should not be the only defense against overvoltage, overcurrent, or thermal runaway. Be sure to mention voltage, current, and temperature monitoring, state estimation, balancing, charge and discharge limits, contactor control, fault detection, diagnostics, communication, and functional safety responsibilities. Question 5. How do you estimate state of charge in a lithium-ion battery? I typically combine Coulomb counting with model-based correction. Coulomb counting integrates current over time, but sensor offset and capacity uncertainty create drift. An open-circuit voltage relationship can correct that drift after sufficiently long rest, although it is weak in flat voltage chemistries. A Kalman filter-based equivalent circuit model can combine current, voltage, temperature, and predicted behavior. I would validate the estimator across temperatures, aging levels, drive cycles, sensor tolerances, and different initial charge conditions. Discuss Coulomb counting, open circuit voltage mapping, equivalent circuit models, current sensor errors, temperature dependence, initialization, rest periods, observer correction, and validation across chemistry and operating conditions. Question 6. What is state of health, and how would you estimate it? State of health describes how a battery's present capability compares with its beginning of life condition. Capacity retention and resistance growth are common indicators, but power capability and energy efficiency also matter. I would estimate SOH using periodic reference measurements, incremental capacity features, pulse resistance, and model parameters extracted during normal operation. Temperature and recent load can distort those measurements, so I would compensate for operating conditions and report confidence bounds instead of presenting an unjustifiably precise single value. Focus on capacity fade, resistance growth, power capability, diagnostic features, reference tests, model-based estimation, data-driven methods, aging conditions, uncertainty, and distinguishing degradation from temporary operating effects. Question 7. How would you design a battery thermal management system? I would first quantify heat generation from ohmic losses, polarization, and entropic effects across the duty cycle. Then I would choose cooling based on heat flux, packaging, cost, and allowable temperature gradients. Liquid plates usually provide better uniformity and power capability than air, but add plumbing and leak risks. The system should support cooling and cold weather heating, monitor representative cell temperatures, and prevent propagation if a cell enters thermal runaway. I would validate both steady-state and transient conditions. Mention heat generation sources, thermal resistance, cooling uniformity, liquid or air cooling, operating temperature range, gradients, transient loads, cold weather heating, sensors, controls, and runaway containment. Question 8. What causes thermal runaway, and how can it be mitigated? Thermal runaway occurs when self-heating reactions exceed the cell's ability to reject heat. Triggers include internal shorts, overcharge, crushing, external heating, and manufacturing defects. Mitigation begins with prevention, robust separators, accurate limits, current interruption, thermal monitoring, and fault isolation. At pack level, spacing, barriers, vent pads, cooling, and propagation-resistant materials reduce consequences. I would verify the design through nail penetration, crush, overcharge, thermal exposure, and propagation testing under relevant regulatory requirements. Cover triggering faults, exothermic reactions, separator failure, gas generation, propagation, prevention layers, electrical protection, thermal design, mechanical venting, detection, and abuse test validation. Question 9. How do lithium-ion batteries degrade over time? Battery degradation usually combines loss of cyclable lithium, loss of active material, and increasing impedance. Say growth consumes lithium, while particle cracking and structural changes reduce active capacity. High temperature accelerates calendar aging, and high current, low temperature, or charging at high society can cause lithium plating. I separate calendar aging from cycle aging because their drivers differ. To diagnose mechanisms, I compare capacity, resistance, differential capacity features, and post-test evidence across controlled temperature and society conditions. In your answer, explain loss of lithium inventory, active material loss, say growth, lithium plating, impedance increase, mechanical damage, calendar versus cycle aging, and temperature, SOC, and rate effects. Question 10. What is lithium plating, and how would you detect or prevent it? Lithium plating is metallic lithium deposition on the graphite anode instead of normal intercalation. It is promoted by low temperature, high charging current, high society, and elevated cell resistance. Plating can reduce capacity, increase impedance, and create internal short risk. I would prevent it with temperature-aware charge limits, preheating, appropriate electrode design, and conservative fast charge control. Detection can use reference electrodes, incremental capacity analysis, relaxation behavior, model residuals, or destructive postmortem analysis during development. Discuss metallic lithium deposition during charging, low temperature and high rate conditions, safety and capacity consequences, voltage behavior, differential signals, temperature limits, charge current control, and validation methods. Question 11. How do you calculate battery pack energy, capacity, and power? For identical cells, series connections increase voltage, while parallel connections increase ampere-hour capacity and current capability. Nominal pack energy is approximately voltage multiplied by ampere-hours, but usable energy must account for voltage variation, SOC limits, efficiency, temperature, and aging. Power is constrained by both current and voltage, plus cell resistance, busbars, contactors, and thermal limits. I would calculate continuous and peak ratings separately, then validate them against the real duty cycle rather than relying on nominal specifications. Be sure to distinguish series and parallel connections, nominal versus usable values, voltage windows, current limits, C rate, efficiency, pack losses, aging, and continuous versus peak power ratings. Question 12. Why is cell balancing necessary, and how do passive and active balancing differ? Cells naturally diverge in capacity, resistance, self-discharge, and aging. Without balancing, the highest voltage cell can limit charging while the lowest voltage cell limits discharge, reducing usable pack energy. Passive balancing removes excess energy as heat through resistors, making it simple and inexpensive. Active balancing transfers charge between cells, improving efficiency but adding hardware and control complexity. I select the strategy based on pack size, mismatch, balancing time, thermal budget, and the required lifetime performance. Explain cell mismatch, weakest cell limitations, passive resistor bleeding, active energy transfer, balancing thresholds, energy efficiency, thermal impact, complexity, balancing timing, and pack level safety implications. Question 13. How would you investigate an unexpected increase in cell resistance? I would first reproduce the result under controlled SOC, temperature, rest time, and current pulse conditions. Measurement errors from contacts, sensors, or timing can resemble cell resistance growth. Next, I would compare DC pulse resistance, AC impedance, capacity, and relaxation behavior against baseline cells. I would examine manufacturing records and operating history for cold charging, overcurrent, or thermal exposure. Finally, I would use tear-down and microscopy if needed, distinguishing reversible polarization from permanent damage before recommending a corrective action. Mention confirming measurement accuracy, controlling temperature in society, pulse testing methods, baseline comparison, electrical connections, aging history, impedance spectroscopy, failure analysis, and separating reversible from permanent effects. Question 14. What battery tests would you perform before releasing a new cell design? I would start with capacity, energy, power, efficiency, impedance, self-discharge, and temperature characterization across the specified operating window. Life testing would include representative cycles, high and low society storage, fast charging, and elevated temperatures. Safety validation would cover overcharge, external short, crush, nail penetration, heating, vibration, and venting behavior as applicable. I would include multiple production lots and statistical limits, because a few excellent prototype cells cannot establish manufacturing capability or reliable field performance. Cover electrical characterization, capacity, power, efficiency, impedance, cycle life, calendar aging, temperature performance, abuse testing, manufacturing variation, statistical sampling, and acceptance criteria. Question 15. How does fast charging affect battery life and safety? Fast charging raises current, heat generation, polarization, and the risk of lithium plating, especially at low temperature or high society. I would use a temperature and SOC-dependent charging profile, higher current in the efficient middle range, followed by tapering near the voltage limit. Active cooling and accurate cell monitoring are essential. The best design balances customer charging time with life targets, because pushing maximum current continuously may achieve impressive short-term performance while accelerating degradation. Discuss high current, heat generation, polarization, lithium plating, SOC-dependent charging, temperature dependence, tapering, cooling capacity, charger communication, and the trade-off between charging speed and durability. Question 16. How would you diagnose a battery pack that loses range in cold weather? Cold weather increases electrolyte resistance and slows electrode kinetics, so voltage limits are reached earlier and available power falls. Vehicle heating loads can further reduce driving range. I would reproduce the complaint using controlled temperature, route, payload, tire, and HVAC conditions, then separate energy consumed by propulsion from thermal loads. I would inspect resistance, usable capacity, SOC estimation, and preconditioning behavior. Improvements might include better insulation, coolant heating, smarter preconditioning, revised limits, or more capable thermal hardware. In your answer, separate reduced electrochemical kinetics, increased resistance, lower usable capacity, cabin heating demand, SOC estimation error, charging limitations, thermal conditioning, and controlled cold temperature testing. Question 17. What is the difference between calendar aging and cycle aging? Calendar aging occurs while the battery is stored or lightly used, driven mainly by time, temperature, and SOC. Cycle aging results from charge and discharge activity, including depth of discharge, current, mechanical stress, and thermal exposure. To separate them, I would run controlled storage groups at several society and temperature points alongside cycling groups with matched conditions. Periodic reference tests would track capacity and resistance. In real products, both mechanisms interact, so lifetime models should combine their contributions carefully. Be sure to define both mechanisms, explain time, temperature, SOC, depth of discharge, C-rate, and rest effects, and describe how you would design experiments to isolate each contribution. Question 18. How do manufacturing defects affect battery performance and safety? Manufacturing variation can create weak cells, elevated self-discharge, resistance spread, or internal short risk. Examples include metallic contamination, coating non-uniformity, separator damage, moisture, poor tab welding, and electrode misalignment. I would control these through clean processes, inline vision and electrical inspection, formation data screening, leak tests, statistical process control, and lot traceability. A strong quality system links process parameters to cell performance and investigates outliers rather than hiding them through aggressive pack-level balancing. Discuss contamination, coating non-uniformity, burrs, misalignment, poor welding, moisture, separator damage, formation quality, inspection methods, process controls, traceability, and the connection between defects and field failures. Question 19. How would you design a battery pack for crash safety and electrical isolation? I would treat mechanical, electrical, and thermal safety as connected requirements. The enclosure must protect cells during intrusion while controlling deformation and providing safe vent paths. High voltage protection includes fuses, contactors, pre-charge, service disconnects, interlock monitoring, and insulation detection. Crash signals should open the appropriate circuits quickly, while low-voltage systems preserve diagnostics. I would validate the complete pack through crash, vibration, water ingress, dielectric, isolation, and post-crash energy tests, not component tests alone. Mention enclosure strength, cell restraint, crush zones, high-voltage isolation, fuses, contactors, service disconnects, interlock circuits, insulation monitoring, venting, crash detection, and relevant validation tests. Question 20. Describe a battery engineering failure you investigated and how you used data to solve it. I would structure the investigation around containment, evidence, reproduction, root cause, and verification. For example, if a subset of packs showed premature capacity loss, I would quarantine affected lots, compare logs and formation data, and control temperature, SOC, and duty cycle during retesting. I would use statistical comparisons to identify a meaningful variable, reproduce the failure, and confirm the physical mechanism through teardown. Corrective action should include design or process changes, followed by accelerated validation and monitoring of field results. Focus on structured problem definition, safety containment, data collection, hypothesis testing, failure reproduction, statistical comparison, root cause tools, corrective action, verification, and lessons transferred into design or process controls. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.